Good morning. We have a final exam coming up, and so what I'd like to do is just take a look at a set of problems that showed up on a previous year's final exam. Of course, our final exam will be different from this, but it does give you a feel for what a set of problems for a final exam might look like. So you can see that there's 8 problems. They don't have any separate parts to them. They don't have A, B, C, D, E going on. It's just 8 straight questions. There's just one item that they're each asking for. It could be a series of steps that are going to be required to answer these questions. But in any case, I found over the years that this works pretty well. So the averages on the final tend to be roughly the same as the averages have been on the midterms. So students do, roughly they do just about as well on the final as they've done on the midterms. Of course, it varies, from student to student. Some students do better on the final, some not as well. But let's go ahead and take a look at just a set of problems. Now, when I'm putting together a set of problems for the final exam, ideally I would like to draw on kind of a range of different topics. It would be nice to get a lot of different topics included. It's not always possible. Sometimes it can be pretty difficult to get a lot of things included, but what I would like to do is have the final exam sample as broadly the topics that we've looked at during the semester. So of course, this is a good set of problems to look at, and the real feature here, as I've mentioned, is that it gives you an idea of what the format is like. On the other hand, you're going to want to go back and do more thorough review. I would say start with the midterms themselves. Go back and look at the midterms that we've had this semester, and then go back and look at the practice midterm, the midterm sampler problems for each of the midterms. There are more of those. It's going to give you a wider range of topics that might possibly show up on the final exam. So look at those earlier midterms, the midterm samplers, and then go back and look at homeworks and examples from class 2. As much as time permits, go back and review as broadly as you can. So I'm going to go ahead and just get started here, I guess. And so got 4 problems on the first page, 4 on the second page. The first problem is saying that we have some charges set up. They're at the corners of a square. So we've looked at some of these problems where we have maybe equal amounts of charge placed in some kind of a symmetric configuration, and then it asks about force or field or electric potential energy maybe. Let's take a look and see what they're asking for on this one. Here they're asking for the electric field and electric potential at the location of center of the square. Now, we've seen problems like this where there could be a fair amount of cancellation. Maybe things cancel, maybe they don't. That's certainly one of the possibilities. So let's take a look and see what happens on this problem. Now, the way the charges are arranged here, notice that the plus charges are on opposite corners. And that says that if I were to place an additional charge, I bring in one additional charge at the center, that charge at the center would feel forces from both of these. Those 2 forces would cancel out. So the net effect of having 2 positive charges placed here, if I'm looking at a point right between them, is that the electric fields would cancel out. These 2 charges are negative, but the same sort of thing's going to happen then. So if we placed an additional charge at that location, the forces would cancel out. And that tells us that the electric fields will also cancel out. So what we can say here is, I should have written down at least the formula for the electric field, but in this case, I've got vector addition of the 4 electric fields. And what we're seeing is that, well, I've numbered these, 1, 2, 3, 4, and 1 and 4 are going to generate electric fields away from the charge. These are positive charges. Positive charges, Q1 and Q4. There's going to be an electric field at that location. There is an effect from charge 1, and we represent that as an electric field pointing away from charge 1. Similarly, for charge 4 at that location, there will be an electric field, and it will be directed away from charge 4. Since the charges are all the same amount, now they'd use little q, I switched over to big Q, but since those charges are all the same amount, we'll get a perfect cancellation. Now, if you get a problem like this, of course there's no guarantee they're going to cancel to 0, so you've got to take a look at the problem and see what's going on. And even if you do determine that it's at 0, you've got to explain yourself. So you've got to show the reason why. So I can't just write down 0 here. I've got to give some kind of a justification for why all the electric fields will cancel out. So definitely on the final, as with all the midterms, you've got to show your work. If I can't see that you're explaining how you've gotten your answer or justify the reasoning that you're using, then I can't really provide any credit for that problem. So make sure that when you answer these, you are showing work of some sort. What I've done here is I've used a diagram. Again, it probably would have been better if I wrote down a formula, and then I could refer to that and say, all the charges are the same magnitude. The distances from the center out to the charges are all the same, because we're at the center of the square. And because we have the same charge along the diagonals, the positives are along one set of diagonals, the negatives along the other. The E1 and 4 will oppose each other and cancel out. The E2 and the E3 will cancel. You've got to have at least that much explanation. Now, in terms of the electric potential, what we've seen in other examples is just because the electric field goes to 0 doesn't mean the electric potential goes to 0. Those are two different questions. Now, in this particular example, let's see, we're at the center. Remember that the electric potential does not depend on direction. It only depends on charge and distance. The electric potential V is not a vector. It's a scalar quantity. And so here I'm just adding numbers together. Notice there are no vector signs here. Within the diagram, what I have to think in terms of then is I have this much positive charge located this distance from the center, and that's going to determine the electric potential contribution due to charge 1 at that location. Now here, if I took charge 1 and charge 4, they actually reinforce each other. So at the center, the effect from charge 1 and charge 4 would double the overall electric potential. What's happening here is we're still getting cancellation, but the cancellation is happening because if I'm standing at the center, I'm a certain distance away from this positive charge. I'm an equal distance away from this negative charge, and the magnitudes, there's just as much negative charge as there is positive charge. And that exactly cancels out. Directions don't come into this. And so just adding those numbers, the effect from the positive charge plus the effect from the negative charge, those will cancel out. Over here, the positive and negative charge effects at the center, again, will cancel out. So what I've written here is that the plus charges and the minus charges are opposite. And so what will happen is when I add all the effects together, they'll add up to be 0. Okay, make sure that you're showing your work. Make sure if there's a problem like this, you provide some sort of an explanation. Diagrams are great. A couple quick sentences are really good for this. So that was problem 1. Let's move on to problem 2. Problem 2 says that we have a couple of light bulbs. One that, we went to the store and we bought a couple light bulbs and we're bringing them back and we're plugging them into this circuit. And they're designed for 120 volt outlets. So it does sound like it's kind of a standard light bulb being plugged into a standard wall outlet. One of these is rated at 75 watts when it's plugged into 120 volts. The other one is rated at 25 watts what's the overall resistance when I have these two lights turned on? How much resistance is in the circuit? So what I did is I started with kind of a diagram of the circuit. Now, since they've given us the 120 volts and the numbers they're giving in terms of 75 watts and 25 watts, all of that just reminds me of a standard outlet. Now, standard outlets are AC. They're alternating current. But remember, all the formulas that we've derived using DC, using direct current, we modified those. We defined RMS voltages, and we defined average powers, and found out we could use the very same formulas for the wall outlets. The alternating current from the wall outlets vary as a sine function. And when we carried out the mathematics of that, we showed that we could get the very same set of formulas with the understanding that P is the average power and V and I are RMS values. So I just go ahead and use the same formulas. So let's see how that would work. Now, if you remember, the intrinsic property of the light bulbs is their resistance. If I build a light bulb, I can't guarantee a certain power or guarantee a certain voltage or a certain current. I have to plug it into a particular voltage, and then it's the resistance of those light bulbs that will determine how much current there is and how much power will be operating. So I wrote this much down. I said that the power for each one of the light bulbs, we can set the power equal to the voltage times the current. Now the currents aren't given, so I switched that over into another one of the formulas that we've been using. So the power of an electrical device can be given by V squared over R. Now that's really handy for something plugged into a wall outlet, because I know the voltages there are going to be 120 volts, and that's what we've been told. So this formula, this extended formula, allows me to go in and solve for R. So I did that. I said that for resistor 1, I put in V1 squared over power 1. That's 120 volts squared over 75 watts. Now when I carried out that calculation, I found that the resistance of light bulb number 1, it's got to be 192 ohms. Why don't they just write that on the package, right? Because nobody cares what the resistance is. People want to know when they plug this light in, how bright is it going to be? And so they're saying 25 watts. Anyway, we have used our formulas that we've developed and derived in order to determine, oh, this is how much resistance is actually in that light bulb. Using the very same formula, this time applying it to resistor number 2. So I'm going to take the voltage square, divide by the power. Did I get these? This is the 75 watts. Okay. For the first one, I think we're fine. Yeah. So the 75 watt one is the one that was given first. So this is 75 watts. It's light bulb 2, resistor 2, that we're going to calculate from the 25 watts. And notice what's going on here is we're also getting a chance to go in and see how appliances work. So appliances are always, when we plug different things into outlets, every new device that we plug in, they each go in parallel. And so when I'm putting them all into parallel, then they're all being directly connected to this 120 volt source that PG&E is providing, I guess. 120 volts divided by 20. So this is saying that it's 576 ohms. Now, what's going to happen here then is, because R1 is lower in resistance, R1 will allow more current to come through, and more current at the same voltage means more power. So if I've got more current going through, same voltage, I'm going to get more power. That's going to be a higher power device. The resistance here is higher, and so actually when the resistance goes up, there's less energy being used. Resistance goes up, that prevents the current from coming through, at least not so much current going through, and as a result, this is not going to have as much power. Now, if we were connecting these things in series, it would be a different argument we would have to go through. But our outlets are wired in parallel, and so at least with things in parallel, with the circuits that we work with plugged into our outlets, this is the pattern that we see. Now the answer was, the question was asking about how much resistance then would be in this circuit if I've turned on just these two light bulbs. Well, I've got to combine 192 and 576, but they have to be combined in parallel. Because I have two resistors in parallel, the overall resistance is going to drop. It's not going to be as high because I've provided more paths for the electricity to follow. And so I'm using the formula. I want to pull out the formula that applies for resistors that are in parallel. Following the formula, turns out that the combined resistance, both of those turned on at the same time, is the equivalent of one resistance of 144 ohms. So, questions on that? All right, we have what? We have looked at 24 chapters this semester. You guys are amazing, all of the stuff that you have gone through. So this is like chapters 21, 22, 23, 24, 25, 26, kind of the first part of the course, the first 6 chapters, are represented by those two problems. Now I feel like they're good problems, they're good, important topics that we have looked at the same time that it just doesn't cover everything that we did, right? And when we get to the actual final exam that's coming up, it's not going to be these two problems, it's going to be something different. So it could be something equally as important, but not necessarily related to these two particular problems. And that's why I'm saying study broadly. Make sure you're looking at more than just this final set of questions. Make sure that you're looking at the practice midterms. Make sure you're looking at the actual midterms, homework, examples from class. Okay, let's move on kind of into the next block of six chapters. Part of this is finishing out the electric and magnetic stuff. And so in problem 3, we're generating some electricity. One of the ways that we said, in fact, the way that we said that generators work. So pretty much all the generators, the big scale generators we use in power plants, operate by moving wires through magnetic fields. So magnetic fields get set up, and then in generators, in power plants, we're spinning the generators. Here it's there's nothing spinning. Instead what we have is we've got this one loop? I hope it's one loop. It is, okay, because I know in the key I forgot to, I assumed it was one loop. I've got to read problems carefully. That's one of the problems I run into. So here are the solutions for 3 and 4. I've jumped ahead here. And so here is this rectangular loop coming out. Now what's happening here is these loops, this loop that I have, it's got a bunch of electrons and protons inside. And once those protons and electrons are moving through a magnetic field, they're going to experience a magnetic force. Now, if we've oriented the magnetic field and the velocities in the right directions, then that allows the possibility that we're going to have magnetic forces driving charges through these wires. So let's try this. Let's see, it works like this. So this is my solution for 3. I wrote this down in the corner because they said direction and magnitude. So I should have started with this, but in any case, well, I drew a diagram of the whole setup, which I think is good. But this diagram should have been the next item. So what's happening is the entire loop, all segments of that rectangle are moving to the right. The magnetic field everywhere is into the page, and using the formula for the force acting on charges moving through a magnetic field, it says that there's going to be a force on positive charges in this direction and a force on negative charges in the opposite direction. When we're looking at currents being generated, we're imagining those currents to be generated, assuming that the current consists of positive charge. Now we know that it's actually the electrons in this example. This is probably some copper wiring moving through, and for a piece of copper, the protons are pretty much locked into place. It's a subset of the electrons that are actually able to move pretty freely through the copper, and that would mean that the force on the electrons would be this direction. So let's look at it both ways. Let's see. So as I pull this thing to the left, what's going to happen is at all locations where the magnetic field is, I am going to have a force on protons in this direction. Okay, that direction does not change. Now, when I look at the part outside of the loop, that part is, the charges in there are not experiencing any forces. Okay, so the nice thing about this approach is that we can actually identify exactly where the EMF is coming from. The EMF is not coming from out here. There are no forces on the charges out there. Now, forces on the protons in this direction along the horizontal segments of the rectangular loop, that's not going to push charges along. So the forces on the protons are upwards, and the forces on the electrons are downwards, but that's sideways. And it's not going to move the electrons along that loop. You know where the EMF is getting generated? It's right there. And so I made a big deal about that. I highlighted that. I said this is the location where protons are getting pushed into this direction. Now they're locked in place, but the electrons are getting pushed here. And that's going to generate an EMF. And that was the example that we first looked at. That was the example we really made a big deal about back in chapter 29. So we know that the EMF is getting generated right along here, and we derived the formula of V times B times L for that EMF. So the V is given. The L, we have to do a little reasoning here. They say that the rectangular loop is 90 centimeters by 45. This must be the 90, these must be the 45s. Since it's this segment that we're looking at, it must be one of the 45s. And so I put that into standard units, got that in meters, wrote down my magnetic field. V times B times L is giving us an EMF of 2.48 volts. That's how much EMF is being generated due to the magnetic force pushing on the electrons through that piece of copper. Now, the direction of the current, we said, is as if the charges were positive. So the electrons are moving this way, but the current, I, we define in the opposite direction. So the EMF then is being driven in this. If this were a battery, this would be the positive terminal, that would be the negative terminal. Okay. Questions on that? All right, so now we've got the EMF figured out, but what they actually wanted was a bit more. They said that the wire has a combined resistance of 25 ohms. They want to know how much current is being generated. Well, current's going to come from EMF over R. So whether or not the EMF is being provided by a battery, a chemical reaction inside a battery, or whether, if the EMF is being generated in a generator using magnetic forces or electric forces. We've looked at examples of both. This one is definitely an example of using magnetic force to push charges. That works out to be, I ended up with 99.0 milliamps. That's how much current we're going to get. And I guess that's it. So this is showing the direction. Not yet. This is showing the direction. So that means that the EMF is directed here. It's along that segment. And the current will get pushed in the direction of the EMF. There's just the one EMF in the circuit. So the current will follow the direction of the EMF. So the current is going to be looping, same amount of current at every location. It's going to be looping around that wire. Now let's take this back. Let's bring this back to a time when the entire rectangle was, maybe the magnetic field is just here. So here I am, the rectangle's going through. At what times are we actually generating EMFs? Well, when the rectangle's out here, there are no forces at all to generate the EMF, so there's no EMF here. When this edge goes into the magnetic field, that's going to start generating an EMF in that direction that we just outlined. And since there's an EMF here and it's not being opposed anywhere, when it first enters the magnetic field region, we're going to have a current going in this direction due to the EMF in the leading part. Now, what happens when the whole thing is in the magnetic field, if the magnetic field is wide enough, is that we would have opposing EMFs, and the EMFs would cancel each other out, and again the current would drop to zero. And then once this leading edge exits the magnetic field, then the EMF on this side is gone, and all we're left with is an EMF on this side. So the current is going to get generated during the intervals where we have an EMF on one side, but it's not being opposed by the other side. So it's while part of the loop is in the magnetic field and part of it is not, that we'll end up with EMFs, and that's where we'll end up with the currents. All right, questions on that? All right, and then I'm wondering, it seems like we should have had one more problem that came from the electric and magnetic chapters. Anyway, this may be jumping ahead just a bit and picking up an additional problem from, this is going into light, and it's looking at a couple of lenses. Now, one of the lenses, the first lens here, is converging. It's followed by a diverging lens. They are giving us, they're kind of giving us all the information. They're saying that we start with an object, and then we're going to let the light from that object pass through lens number one and create an image. And then that image is going to get picked up. That's going to become the object for the second lens. So this problem I just divided into kind of two columns. In fact, it's a lot like the lab that we did. If you think about it, this is a lot like the lens lab that we did when we were measuring the diverging lens. So let's take a look and see. So for lens number one, we're told that the very starting object has a lateral size of 3 centimeters, and it's got a DO of 12 centimeters. It's placed 12 centimeters ahead of the converging lens. And that this did I get all the numbers right? Okay. Focal length is 5 centimeters. I'm just checking here. So I can use, our standard formula here. So I'm bringing out the object distance, image distance, focal length formula. And solving that, I ended up with 8.57 centimeters. So what that looks like so far is, I've got to erase one of these. I didn't get this erased. I apologize. I'll get this taken out. This was a lens that I drew in my diagram, but then I realized I had gotten the scale incorrect. So I intended to drop that one out. This is the actual lens. So this is lens 1 here, and this is lens 2 here. I'll have to remember to go back and get that corrected. All right. So this is the 12 centimeters here, and then the 8.57 brings us to here. Now, remember, lens 2 is placed a distance of 8 centimeters from the converging lens. So the image that we just placed from lens number 1 is just a little bit beyond lens number 2. Not very far, but a little bit beyond that. Now that says, let's finish lens 1 here. So we've got the DI figured out. We can go through and calculate a magnification. Magnification works out to be negative 0.714. Let's take a look at the drawing. Yeah, it seems about right. So it's inverted. That's the minus sign. And it's, it's about 70% the size of the image. And using the magnification formula, it says that the image is 2.14 centimeters in size, in lateral dimension. Now, the original object was 3, and so the 2.14 is it's a reduction in size. We multiplied by that magnification of 0.714. All right, here is the tricky part. How do we pick up information that we've solved for in lens 1 and bring that over and get the formula started for lens 2? So, first thing we can point out is that image that was generated by lens 1, that's going to be the object for lens 2. So I can just start with that very same number. Nothing needs to be changed there. Now for lens 2, the problem is telling us that it's got a focal length of minus 20 centimeters. So that's the focal length that's given. It's diverging, but it's not very diverging. That's a pretty long focal length compared with the 5 centimeters, I guess. In any case, here is the trickiest step right here, and that is, what should I use for DO? Well, let's go back and look at the diagram. What we found was that the image from lens 1 landed just beyond where lens 2 is located, and that says that whatever that distance is right there is going to be DO, and it's going to be a virtual object. The DO is going to be a negative number. So we can take that 8 centimeters and subtract off the 8.57, and that gives us a DO of negative 0.571, where the negative sign says that it's a virtual object. It's out beyond where the second lens is. So again, this is basically the lab that we did, right? Where we were doing the measurements of the diverging lenses, and we were using virtual objects, identifying the DOs and DIs for a diverging lens. All right, so we then can, once we've got this number for the DO, we can solve back into our standard formula to find the DI once again. And the DI worked out to be 0.588. Now that's interesting because the DO is at 0.571. This is at 0.588, but it's positive. What does that mean? Well, a positive image would be on the side of the lens where the light is exiting. And so the image is just beyond where the object is located. Now the object is virtual, and it's got a minus sign on it, but the image is real because it's got a plus sign here. When we do the magnification, it's 1.03. The magnification here is going to get multiplied by that object height, 2.14, to give us 2.20. The diverging lens did not introduce an inversion. So we did have an inversion with that first lens, but we did not have an inversion on the second lens. So it remains oriented opposite to the original object that we started with. All right, questions on any of that? So with these lenses, as you know, the lenses are, the lens formulas look fairly straightforward, but you've got to be able to keep the sign straight. And in this case, having multiple lenses meant that we really had to pay attention to that offset. The two lenses were set 8 centimeters away from each other, and that number had to get subtracted off or taken into account in figuring out the DOs. All right, I'm going to go ahead. I think I'm just going to go ahead and do this all in one session. So here we go. Here's the next 4 problems, and here are solutions for the first 2 of those. Problem 5 is saying that we're taking light from a transition in hydrogen, specifically the n equals 4 to n equals 2 transition in hydrogen. We're passing that through a diffraction grating. This is a D value that's given, and then we're supposed to predict the angular locations. So now we're looking at the interference, well, yeah, the interference effects of light and what kind of interference patterns are we going to end up with. So let's start with formulas related to hydrogen. We know that with hydrogen, to find the energy of the electron quantum states, we can take minus 13.6 eV and divide through by the quantum number for that state. So I drew a quick diagram here. This would be ionization. Here is state 4, state 3, state 2, state 1. We're looking at a transition from 4 to 2. So the electron energy in the fourth quantum state is a binding energy of 0.850 eV. And in state number 2, the binding is quite a bit higher. It's 3.40 eV. Now the difference between those two energies of the electron will tell us how much energy the photon will have that gets created during this transition. So an electron, I should have drawn an electron in here, the electron drops from state 4 to 2, that energy is conserved in this process, and the energy shows up as a photon. So with an energy of 2.55, we can calculate the wavelength. That would be hc over energy. Hc is 1240 eV nanometers. That works out to give us a wavelength of 486 nanometers. So here is the diffraction grating. So I thought, well, I better draw the diffraction grating in. Here's the diffraction grating with all those little etchings going on, all those slits going on. The formula that we use for the diffraction grating is a d sine theta equals m lambda. Remember that the diffraction gratings got misnamed. They're really multiple slit interference devices. They're not really based on diffraction. They're based on multiple slit or multiple source interference. And so we're using the very same formula that we've used for two slits, for example. And we're going to go through and solve for the angle. That's what they want. So sine theta should be m lambda over d. Now I got to get the d information solved from the information given. So they tell us that this diffraction grating has 4,000 lines per centimeter. So the diffraction grating, we can take that 1 centimeter and divide into 5,000 pieces, and then convert from centimeters into nanometers, and show that the diffraction grating that we're using in this example has a d value. The distance from one line to the next in the grating is 2,000 nanometers. Okay, and that's really small. You'd have to have some, precision machinery to carefully make these etches in the diffraction grating material. So once we've identified what the value of d is, we can come back and plug into the formula. So for the first order, peak for this particular wavelength of light coming from a hydrogen transition, m is equal to 1. The wavelength we're going to use is 486, and the distance between slits in the diffraction grating is 2,000. Solving for that, I ended up with 14.1 degrees. And then moving on to second order, everything stays the same except for m. So the m now is going to be 2. Plugging that in and solving for theta, this one turned out to be 29.1. So this is kind of a nice problem in that it is a diffraction problem, a problem in multiple source interference, multiple slit interference, but it brings in some atomic physics. So it brings in some of the atomic physics that we've seen for hydrogen. So, there's an example, maybe a good example of bringing in different ideas from different parts of the course and combining them into one example. Okay, here's another example here on 6. Here it's saying that we could have neutrons because of the reactions going on in the sun. There's a possibility of neutrons maybe coming off of the sun, and neutrons could pose a threat, could pose a health threat if we're exposed to large amounts of neutrons. Now, the sun also has a lot of electrons and protons that come off at high speed, the magnetic field of Earth helps direct those away from the kind of the mid-latitude regions and redirects them towards the polar regions. But the neutrons would be able to, the electrons would be able to pass through more readily. And so, how much kinetic, this is kinetic energy. I solved for speed. I got to go back and add on to this. Sorry about that. Let's find out how fast the neutrons would have to be traveling. And then we can, from there, I'm guessing you guys can do the kinetic energy calculation, but I'll have to get that added in. So, the neutron itself is not stable. A neutron isolated from a nucleus actually will undergo decay. We could think of it as radioactive decay, but it undergoes decay, and 10.4 minutes or 624 seconds. Now that's at the neutron's at rest. Relativity tells us if it's traveling at some high speed, it's going to survive longer. So there's going to be a time dilation effect. So this problem is including this time dilation effect from relativity as well as looking at radioactive decay. So here we go. The radioactive decay says, formula says that the number surviving after a certain amount of time is going to drop off exponentially. Now the problem asks about the probability that half of these would reach the Earth. How fast would a neutron need to be traveling in order to have a 50% chance of reaching the Earth? Well, we can set this factor equal to 1/2. That's equivalent to saying, what speed would the neutrons need to be traveling if they're going to, half of them are going to reach the Earth. So I set the exponential factor equal to 1/2. I inverted those. This becomes a plus sign, that becomes 2. And then I took a natural logarithm. That undoes the e, and it leaves us with t over tau is ln of 2. Now, I called this the lifetime, the 624 seconds. That's in the rest frame of the neutron. But our tau is going to be time dilated. So, let's see. The time that it takes to reach Earth is going to be the distance divided by its speed. And up here, we're saying that t also can be written as the natural log of 2 times the lifetime, and then that lifetime needs to be time dilated because of relativity. So when I gather together everything in that formula, in that algebra, I'm getting gamma times v, those are both measures of velocity, is equal to d divided by the ln of 2 divided by the lifetime in its own reference frame. So those are the numbers we actually have. Now I took out the v, and in place of v I wrote in a formula for v in terms of gamma. Now if you remember from relativity, I think I've mentioned this before, that in relativity we end up with these kind of formulas where we've got a factor of v and a factor of gamma, and we just have to decide, do we want to solve the problem in terms of v, do we want to solve it in terms of gamma? And I'm going to say almost always solving in terms of gamma is easier. Okay, so that's what I did. I removed the v and substituted in an expression in terms of gamma, and then I proceeded to solve for that. What I ended up with was this gamma squared minus 1 square root is 1.156. I solved for that. I solved for gamma. And then finally I solved for v, 0.756 times c. So it's really, really unlikely neutrons coming off the sun would have velocities anywhere near that number. So very likely we are doing pretty well. I guess I should double check. I should look that up and make sure that that's not happening too frequently. Now, as I mentioned, this is the velocity. That's what I solved for. So again, read the problems. This is pretty good though. If you accidentally did this, you would get most of the credit. But it does ask about kinetic energy. Kinetic energy for the neutrons comes from taking gamma and subtracting 1 and multiplying by mc squared. So it's not too much addition to what we have here. In fact, I'm kind of thinking having the velocity is more interesting than having the kinetic energy. All right, let's move on to those last couple of examples. Problem 7 says we got a microwave oven. This is something really basic here. This is just counting photons. So it says the microwave oven apparently operates at 700 watts, and all of that goes into generating photons within the microwave part of the spectrum. And so we want to find out how many photons are being generated. When I look at I read the owner's manual on my microwave oven, and it says that the photons have a wavelength of 12.2 centimeters. So what we can do is, I'm going to start with that, 12.2 centimeters. I did this energy thing with hc over lambda. Now notice this is in centimeters, it's not in nanometers, so I got to be a little careful. I did go ahead and use the 1240 EV nanometers, but then I had to put in a factor of 10 to the 7. When I did that, and then converted into joules, I ended up with each photon within this microwave oven. Each photon has an energy of 1.626 10 to the minus 18 joules. That's the photon energy. Each photon has that much. If the microwave is listed as 700 watts, that would be 700 joules per second. And if that's all going into photons, I can take the 1.626 10 to the minus 18 joules per photon. The joules cancel out. What I'm left with is 4.3 10 to the 20th photons per second. All right. Now, that's a big number. If we compare that with Avogadro's number is like 6 times 10 to the 23rd. So this is like 1,000th of a mole of photons every second. So it would take like 1,000 seconds, and it's going to take 10 or 15 minutes or something to produce a mole of photons in my microwave oven. Anyway, it's an example of counting photons. Let's go ahead and take a look at this last problem. So this is looking at some more nuclear physics, and it says that these following isotopes have some of the highest nuclear binding energies of any isotopes known. And we're guessing at this point, we haven't missed any of those really stable isotopes. If you're curious sometime, you can go into search Wikipedia and search for isotopes of iron, for example. And there's a table for every element, isotopes of. Just look up the isotopes of your favorite element. And it's just got this long list of isotopes, and pretty much they're all there. I mean, the ones that might be discovered at this point are the really, really short-lived ones. But these are really, really stable. So anyway, these are among the most stable isotopes in nature, in the universe. And using the masses given here for the neutron, proton, and electron, what we can do to calculate the binding energies is take each one of these, count how many protons, how many neutrons, how many electrons do they have. Now I know the textbook does this shortcut, where instead of counting protons and electrons, they combine them into the equivalent of a hydrogen atom. That's okay if you want to do that. I still prefer just counting all three of these individually, just to keep reminding myself of that we're combining protons and neutrons to form the nucleus, and that the nuclear binding energies we calculate actually are going to include some effect of electric and magnetic binding energies of the electrons. So again, it's going to be dominated by the nuclear force energies. What we can do is we can add these masses together, and that's what I've done for each of these, so they're all kind of it's a bit repetitive here. This is adding up the mass of all of the protons, neutrons, and electrons. This is subtracting off the mass of the manganese 55. This is the missing mass. Remember our conversion factor, 931.5 MeV per nucleon. That gives me a total binding energy, 482.1, and then I divide through by the number of nucleons, which would be 55. So dividing through by 55, it says the manganese 55 has a binding energy per nucleon of 8.765 MeV per nucleon. The iron 56 and the cobalt 59, very same pattern. What we see is, I guess we've got, these are consecutive elements, so we're going from 25 to 26 to 27 protons and electrons. And then these two have 30 neutrons, but the cobalt 59 has 32. And what we find is that it's the iron 56 that has the highest binding energy. And that maybe that isotope does have the highest binding energy of all isotopes. That's something I come across from time to time, suggesting that's the case. And I mean, I haven't tried them all, but this certainly looks higher than the most stable isotopes of its neighbors on the periodic table. All right, I think that wraps everything up. So again, I think it's a useful set of problems to look at, but make sure you are looking and preparing more broadly than just looking at these 8 problems. This is a nice set of problems. It appeared on a final exam, several years ago. It's a good chance to come in and practice just the format of the final exam, and and take a look at some good examples that are a good review of what we've done during the semester. Okay, any questions at all, just stop by office hours, let me know, and we'll get those looked at.